Okay, chemistry. So we're in chapter 10 and we're taking a more in-depth look at states of matter. We already went through gases last time. Remember the kinetic molecular theory? And gases, remember the ideal gas, what that represents, and real gases, some of their properties and how those properties are explained by the kinetic molecular theory. Right now, we're going to take a quick look at liquids. Well, not quick, it's quite a bit in depth. In understanding liquids, recall that in the kinetic molecular theory, one of the assumptions, I think it was assumption number 4, stated that there are no attractive forces between molecules or atoms of gases. Okay, and that was one of the assumptions we used to explain the characteristics of gases. Well, in order to explain the characteristics of liquids, we recognize that there are definitely attractive forces between atoms and molecules of liquids, of gases too, but not the ideal gas. But for liquids, we admit that because it helps us to explain the properties and characteristics of liquids. So we recognize that there are these intermolecular forces that attract one molecule to another. And these forces determine the properties of liquids. So let's look very quickly at some of these forces. First force are dipole-dipole forces. All right. And those are really easily seen by hydrochloric acid. Hydrochloric acid or hydrogen chloride is a covalently bonded molecule of hydrogen and chlorine, okay? And that's a covalent bond, but as you guys remember, this is a polar molecule. It's polar because chlorine is quite a bit more electronegative than hydrogen. So basically what happens is we have, hydrogen had that one electron to contribute to sharing. Chlorine had 7 electrons and therefore shares electrons with hydrogen, okay? But because chlorine is so much more electronegative, sets up a situation of polarity, not molarity, polarity. And so because chlorine pulls on those electrons harder than hydrogen does, sets up a situation where this side of the hydrogen chloride molecule is slightly negative, and this side, because, I can't see that, let me try that again. And this side, because chlorine's tugging on that electron more than hydrogen does, it ends up being slightly positive. So remember, this is a polar molecule. And these dipole-dipole forces are all about that polarity. So what happens is you have another hydrogen chloride molecule come up here, and because it's also polar, just like this one, all right, this side here that's slightly positive is attracted to that slightly negative side of this hydrogen chloride, okay? And if we have another one over here, all right, okay, this slightly negative side of this molecule is attracted to that slightly positive side. So what we get are these little sort of pseudo bonds of attractive. They're not bonds because they're very easily broken, and it's not like a chemical sharing of electrons. It's more of just a little bit of attraction between these. And when you have this situation, when you have two poles, dipoles, and other molecules like it are attracted to one pole or the other, that's called dipole-dipole forces. London dispersion forces, number 2 here, are quite a bit different. They are much weaker than that, and they are set up within atoms. And they actually, from what I am can tell, and I have read, they're not completely sure that this explains it, but this is the, whoops, this is the model we're going on now for London dispersion forces. And it's kind of weird, but these are the very weakest of intermolecular forces, the very weakest ones. And like I said, I don't think that chemists are totally sure that this is totally how this works, but this is their theory. And again, this is within atoms, single atoms. And remember how we said that electrons, we cannot know their position at any one time. We can only predict where they might be, and that's the case. So what happens on again and off again is that sometimes, so here's this normal distribution or symmetrical distribution. Okay, apparently we're dealing with lithium here. It's got 3 electrons orbiting this nucleus. It's not a very good model, but we'll go with it. Okay, and so this is symmetrical. Okay, the electrons are all equidistant from the nucleus, and they're all equidistant from each other. So that's symmetrical. But because the electrons are free to go wherever they want, sometimes they end up like this in an unsymmetrical distribution, which means that all of them are on one side or the other of the nucleus. Now, when that happens, you should be able to see that the atom itself becomes slightly polar, right? So that this side of the atom is slightly negative and this side is slightly positive because there are no electrons on this side. And so that sets up a situation where this atom can attract another atom that's doing this with the electrons all on one side, so that the slightly negative side of another atom like this would be attracted to this one, or the slightly positive side of another atom like this would be attracted to that one, okay? Those are London dispersion forces. They're a little weird, and they're very weak. Now, the third type of intermolecular forces is a type of dipole force, all right? And we've already talked about this. I think we talked about it in biology, and we might have talked about it a little bit in chemistry here. Okay, but these are hydrogen bonds, all right? Here's a nice picture of it. Perfect example of hydrogen bonding is in water molecules. We've talked because water is a great example of a polar molecule. So it happens, so this hydrogen bonding happens in polar molecules that have hydrogen in it, okay? And basically what ends up happening is the hydrogens set up a situation where they attract other molecules. So we have our water molecule here, and because oxygen is more electronegative, it pulls harder on those electrons, setting up a polarity where we're slightly negative up here, slightly positive down here. So that when another water, what this little diagram is saying is, this line, as you know, is representing the covalent bond that exists between the oxygen and the hydrogen. It actually represents a pair of electrons that are being shared here. You guys already know that, but that's what that means. Okay, but when we have this polarity set up, the oxygen side of the water molecule is slightly negative, the hydrogen side is slightly positive. Well, this slightly positive side attracts the slightly negative side of another another water molecule. And the slightly negative side attracts the slightly positive side of another water molecule. And as we talked about before, I think in biology, I'm sure in biology, I think in chemistry a little bit, this is the reason that water has such high surface tension. Remember dropping drops of water on a penny, and you could just fit a phenomenal number of drops of water on a penny before they broke together? That's because they like to stick together. They like to adhere they like to be cohesive, all right, to each other. They congregate together, and that's because of this hydrogen bonding. And hydrogen bonding, because we're dealing with a dipolar molecule, usually is a type of dipole force. As we've demonstrated with, surface tension and stuff like that, hydrogen bonding can be pretty strong. So these forces, these attractive forces between molecules start to give us a picture of why liquids behave the way they do. I'm going to take a little pause.